Good afternoon. So we're going to continue on looking at compressible steady-state isentropic flow. We derived the isentropic relationships last time that relate pressure, temperature, and density. Today we're going to fill in that missing equation that I put on the board that relates temperature and velocity, that replaces the use of Bernoulli's equation in incompressible flow. So we're still going to have conservation of mass, conservation of momentum, and conservation of energy, but the conservation of momentum equation is going to be in terms of temperature and pressure. And so this thing comes from the Euler's equation. This is where we drew the little fluid element and we looked at the pressure forces acting on it. And this is essentially Newton's laws for fluids. The pressure forces create an acceleration, and that's really what this says. This is the equation that when we said that we had incompressible flow, we said density was constant, and we could integrate this easily because density could be pulled out of the equation. Does anybody tell where that noise is coming from? It's not on the speakers, is it? No, it sounds like it's up above in the ceiling. Some kind of what? Okay, interesting. Sounds like serious. So this equation, density was constant for incompressible flow. We could pull it outside the equations, the integrals, and then it was easy to integrate because we just had P's and V's. But now if density is a function of position, then it varies as well. So we have to deal with that. So we'll use that equation, and then we're going to use the energy equation. And the one that's helpful for us is the enthalpy version. So it has H in it. And the reason that that's useful is that here's dP and here's dP, so we can substitute directly into that form of the equation. The fact that we set the heat transfer to 0, remember this is adiabatic, and so if there's no friction, then we're saying isentropic flow again. There's no heat transfer. It's reversible, so there's no friction. So that's what we have. So what we need to do is essentially some algebra on this and then integrate from 2 points on a streamline. So it's the same old philosophy. We're going to be here, and then we're going to add up all of the pressure differences and velocity differences from here to there. And integration does that incremental adding for us. All right, so if we plug that in there, we get dH on this side. We move that over to the other side. We're still going to have a minus because we have a minus. The minus goes over here, it becomes a plus, but then we get a minus here. So we get the minus V rho capital V for velocity dV. And this turns out really nice because remember, specific volume is this inverse density, so these two cancel out. And that gives us exactly what we want. Over here we have H, over here we have V, and in fact we're going to write dH in terms of temperature because we want flow variables. And so that is, we use the specific heat relationship from thermodynamics that we had before that said a change in enthalpy is C sub P times a change in temperature. And so on the left side we have temperature, on the right side we have velocity, and that's why it's going to give us an equation in terms of temperature and velocity. So this thing is going to relate T1 and V1 was T2 and V2. So there's the equation. It says small temperature changes or corresponding or related to small velocity changes. Interesting. So it says if the temperature goes up, the velocity goes down. If the velocity goes up, the temperature goes down. Because of the negative sign. So if the velocity is going up, the temperature is going to go down. And it makes sense because if the velocity is going up, you have to get the energy to increase the velocity from somewhere. And it's coming from the kinetic energy of the gases bouncing around. So that energy goes out of the temperature and into the velocity and vice versa. With Bernoulli's equation, that related pressure and velocity. So if the velocity went up, the pressure had to go down. So you can think of that as an energy thing. How do you get the velocity to go up? Well, you have a net force that is potential energy that's giving you energy into the velocity, which is kinetic. All right, so we integrate this along the streamline, which just means we add up all those little increments as we go along the streamline from 1 to 2. This is easy to integrate. dt just becomes t. Plug in the limits. And this becomes v squared times 1/2. So I factored the minus 1/2 out. And that's the equation that I wrote on the board last time. Let's rearrange it so we get all the 1s on one side and the 2s on the other. So I moved the minus V2 over to this side. The minus T1 over to the other side. And then this is essentially the conservation of momentum equation. Sometimes in the book, they call this the energy equation, because it did come from the first law of thermo, but it also came from the Euler's equation, which is conservation of momentum. So you can call it either one. The other equations that are like P1 over P2 equals rho 1 over rho 2 to the gamma, I believe I got that right. These are called the isentropic. Because they don't have velocity in them. So you wouldn't call them any kind of momentum equation. They're totally just isentropic flow. They're the property of how P, T, and rho vary in some kind of flow. So that gives us the full set of equations that we can use. We can use this one, we can use the isentropic, we can use conservation of mass for compressible flow. And so if we know areas, we can calculate stuff. If we know velocities, we can calculate temperatures. If we know temperatures, we can calculate densities and pressures, because, and I'm not going to get this one right, this is T1 over T2. I need gamma over gamma minus 1. We're going to use that in a minute. Let me make sure I got it right. Yeah, that's right. So let's do an example. We have an airplane flying at 5,000 feet at 200 miles an hour. So that's how fast the air is coming into the airplane. And then we measure the pressure on a wing. So this is a lot like a problem we had before. What is the velocity? So draw a picture. So out here, the air is coming at the airplane. We'll call this position 1. And the velocity is 200 miles per hour. The altitude is 5,000 feet. And one of those streamlines goes around, and at a position here, we measure pressure, because that's easy to do. It's easy to put a pressure probe in the flow. If you try to measure the velocity, how do you do that? You put a little propeller, and that's going to slow the flow down or affect it. All right, we're not going to assume incompressible flow. We're going to say this is compressible flow. This is pretty close to the borderline, right, of 225. But as the air goes around the top of the airfoil, it's going to speed up because it's going to go around. So this is going to be bigger than V1. So we're not going to say that it's low speed. So this is high speed flow. All right, so here's our picture. What do we know at position 1? We know the velocity, but they've given us the altitude, so we can assume standard atmosphere. Otherwise, how do we solve the problem? We don't know pressure, density, or temperature. So we'll say standard atmosphere. So standard atmosphere at 5,000 feet is 1761 is the pressure. There's the temperature, and here's the density. And where did I get this? Standard atmosphere, table, appendix B, or a standard atmospheric table. So that's the data. And now we look at it and we say, okay, I don't know V2, so I need an equation that has V2 in it. All right, let's write one down. Is that going to help? So we look in our toolbox and we pull out this equation. And we go, all right, we know V1. We know rho 1. Don't know rho 2. But maybe we could use this stuff down here to get rho 2, right? Because I know rho 1, I know P1, I know P2, so I could get rho 2, so I could solve for that. But how about the areas? We don't even have any information about the areas. So I'm going to set that tool aside and say, well, I don't know if I'm going to be able to use this wrench on this particular type of nut, because there's too much unknown. So let's look. Another equation that has velocities in it is that equation we just came up with. Okay, what do I know here? Well, standard atmosphere, I know temperature. I know velocity. I want to find this. How about that? It's not specifically given, but we go down here and we go, okay, I know P1 and I know P2 and I know T1, so I can solve this for T2. So I'm going to need that toolbox, that tool out of the toolbox, and then this set as well. So I can get from isentropic. And you'll find out that this set of equations is very useful if you know pressures, densities, or temperatures. Look at that one first. It doesn't have velocities in it, so if you need velocities, then you're going to have to look at that equation as well. But if you don't have velocities involved, this is probably the equation you're going to end up using down here. All right, so I'm going to set it up, and you guys are going to calculate. So this is the equation we're going to use. It's the P side and the T side. So P2 over P1 equals T2 over T1 to the gamma over gamma minus 1. And I've given you the information. Here's P1, here's T1, here's P2. So tell me what T2 is. You guys work that on your own. Sorry, what? Yeah, do you remember what gamma is? Uh-huh. Did I give you the number before for air? So that's an assumption. We have to say, well, this is air, right? Anybody get it written down? Shout it out if you remember what it is. This is something you need to memorize like right now. I didn't expect you to memorize it before. Anybody have it? What do you have? 1.4. Again, I didn't expect you to memorize it. But you'll, by the time you've used it a couple times, you will. That's for air. If you're on Mars, it's a different value. All right, anybody brave enough? What do you got?
442.
And what's the units? Yeah, and this is easy to track units because it's the same units top and bottom, so all you have to do is look at what the units were there, right? You guys all get that answer? So this is good to practice because in some of the homework you'll need to use this equation. All right, so the next step is to use this equation. So I'm going to give you the data for that, and we'll crunch away on that one as well. So here is T2. It goes in here. V1 is 200. T1 is that number there. And so then we're going to solve for this, right? Except, is there a problem? First, you need to know C sub P. So I'll give you that. And this is, to find this in your book, you have to look at examples 4.11 and 4.12. I wish they had a table in the book, but those values are given in those examples. All right, does anybody see an issue between plugging this velocity in here and plugging this value in here and looking at the units? Yeah, we got to convert it because over there there's feet, right? And seconds. There's no miles or hours in any of the units, and this is not consistent. So you can pretty much guarantee if you're given non-standard units, you got to convert. So we'll convert this. And the conversion is, typically you can multiply 60 miles per, let's see, sorry, 88 feet per second is 60 miles per hour. Is a useful thing to just memorize. All right, do you guys have P1? I erased it, didn't I? Oh, we don't need it. We've already used it. So we just need the temperatures and the velocity V1. So we got all this stuff going around. You guys are plugging in and you're going to give me V2. So what do we have? Oh, yeah, what did I do? Sorry, there's an equal sign there. You got what? 886 feet per, what? 0.5. And so go ahead and convert that to miles an hour. So there's a big velocity change, wasn't there? Notice it was indicated the temperature went down, so that energy went into forward flow. So that's what we expect. So our assumption of compressible flow was definitely valid because look at this velocity. That's really fast. So that must mean the density changed because it's outside our assumption. And in fact, we can calculate the density change from our isentropic equations because that's going to give us the density ratio. So the density change is going to come from the pressure change, which we know. So we had the pressures here that were given to us. And then the density rho 1 we knew from standard atmosphere. So if you punch the numbers on that, put in gamma as 1.4. Changes by about 50 out of 200. So this is about, I calculated this is an 18.5% change. And so that's significant. So that means assuming compressible flow or not assuming incompressible is totally valid. It validates I wouldn't say assumption, it's just a choice. Because we use the compressible flow equations. Let's say that you were watching your TV show and texting and doing your homework, and you said, well, this looks like I could just easily apply Bernoulli's equation. I'm not even thinking about it. I just see the data. I see pressures and velocity information. Right, I know V1 was whatever it was, 293. I remembered to convert this. P1 was, I'll find it here in a minute. $17.61. And then I have P2 over here. That was pressure was measured. Right, so I know those two pressures, I know this, and I want velocity. It'd be real easy to just say, oh, I'm going to use Bernoulli's equation because it relates pressures and velocities, right? So I write that thing down. 1/2 rho V1 squared plus P1 equals 1/2 rho V2 squared plus P2. And if I'm not thinking, I'll go, well, I have rho 1 here and rho 2 here, but I don't know density, so what do I do? Or maybe I don't even think that far. I just go, okay, I know the density is the standard atmosphere. So I'm going to let you guys do this calculation. What is V2 if we use Bernoulli's equation? So we just say, okay, Bernoulli's equation has the information. We know V1, P1, P2, easy. I'll be done and I can go watch the next Netflix episode of Away, which is this show somebody told me about, a mission to Mars. So what do you get for V2? Common mistake here is to forget to square the velocity, so you got to remember to do that. And then when you collect it all together, then you get a square root, right? Somebody new, give me a number. What do you got? You're going to have to shout, I'm sorry. 830. Thank you. Like 0.9, right? So it's off about by that 18%. So it's not exact. You could say, well, it's not really bad, right? But it's still not the right velocity. Now, if we'd gotten 881, then we'd say, well, it looks like an incompressible flow assumption is pretty good. But in this case, it's not. So make sure that you write in your notes, this is the wrong assumption. We just did this to see what would happen. So incompressible. So make sure you write this big, because 2 days or a week from now, you're going back to your notes or maybe studying for your final, and you go, well, why did he do it 2 different ways? So that was just to check to make sure, well, that really was the wrong assumption. So people started flying this fast, and they discovered that when they got up close to about 700 feet per second, that the airplane started behaving differently. That some of these flow equations gave correct answers, but they got weird phenomena happening. And that's because the flow speeds got up near the speed of sound. And we all know, we talk about the speed of sound because we've lived in an era where people fly nearer or faster than the speed of sound. But back then, people had to discover, well, what's going on when an airplane gets going fast? And they had measured how long it takes sound to go from here, you know, like across a football field to the bleachers on the other side. So they knew what the speed of sound was, but we need to talk about exactly what is the speed of sound. And in fact, using our equations of flow, we can calculate the speed of sound. So if we're at 30,000 feet, we can say the speed of sound is like 650 feet per second, because we know the flow properties there, the atmosphere. But to kick that off, let's talk about speeds. So when I was a kid, there was a show on ABC. Back then, there were only 3 channels, NBC, ABC, and CBS, and then occasionally you could get PBS, or you could watch old Batman series reruns on a UHF channel. But on ABC in the afternoon, they had something called the Wide World of Sports. And it was a show about all kinds of cool stuff, sports. And every once in a while they'd talk about people trying to set the land speed record, meaning a car going as fast as it could possibly go on the land. So I looked up the history of that just to kick this off. So this is on the screen here. I'll make it bigger and I'll zoom in some more. So way back in 1898, the first land speed record was set by an electric car going 39 miles an hour. Interesting that the cars were electric there and then they changed to steam and internal combustion. But now we're going back to electric cars. In fact, the buses around campus now are all electric, right? So the speed record, people kept trying, and the first internal combustion engine here set a speed record of 76 because they could get more energy out of that in 1902. And people kept going faster and faster. Oh, by the way, these were done over in Europe in different locations. Except Henry Ford here set a record in the US of 91 miles per hour. And notice it says record is not recognized by European authority. But then people transitioned to going down to Daytona Beach. Here's some other names because there's a nice flat sandy beach. So here's Mercedes. You recognize that name, right? It's a car manufacturer. He went 92 miles an hour. And there's a guy named Vanderbilt. So he's a rich guy driving cars fast. Internal combustion, and then along came a car I remember reading about in a book when I was a kid, the Stanley Steamer. So they switched from internal combustion to essentially putting a train engine driven by steam. So it had a boiler that put steam through pistons and it drove the car. And this thing was incredibly fast. People owned these and would fly through the streets all over the US. This was set at Daytona Beach. The downside to this is you had to go out 20 minutes before you wanted to go anywhere and fire up the boiler and wait for it to get a head of steam before you could go anywhere. But it was fast. Yeah, 1906 till 1909. How many what? Yes, it did. Oh, it went from 109 up to 121. Yeah, it was a giant leap. And then here's another name you recognize, Mercedes-Benz. So he got into the business. Packard, a bunch of other people. So faster and faster, 1920s, 174 miles an hour. That's pretty fast. 200 miles an hour in these cars, guys in Great Britain. And then they switched from Daytona Beach out to the Bonneville Salt Flats in California because they were flatter and it wasn't near the beach. I guess they couldn't drive on the beach as much anymore. So Bonneville, Salt Flats, still internal combustion, and then notice the jump here. In the 1950s, the jet engine was developed and put on airplanes. And so this guy essentially took an airplane. I'll show you a picture of his car. Took an airplane and put wheels on it and went down the Salt Flats at 400 miles an hour. And these other guys, Craig Breedlove, Tom Green, they were setting records. And this was when I was starting to watch it as a kid. This guy set another record in 1965. He went 600 miles an hour. And then finally, this guy broke the sound barrier faster than the speed of sound in 1997. And of course, airplanes had done that way before then, but this was on the ground with wheels on the ground. And here's some pictures of cars. This is a guy that went 104 miles an hour in this car. Notice nothing to protect him if he wrecks. Probably no seat belts or anything. If he wrecked, he pretty much flew out of the car. This is a cool looking car. Very streamlined aerodynamic. It's a British racing driver, Malcolm Campbell, broke the record, 450 horsepower, 12-cylinder engine. This one's cool. Very aerodynamic. And look, it's almost like a submarine, and here's where the pilot or the driver set was in this little bubble here. 394 miles an hour. And this is Craig Breedlove's jet-powered car. So you can look at it and you go, that's an airplane. And they just took the wings off of it and put wheels on it. So he set several records in this. Another jet-powered car, the Green Monster. This was I forgot his name, Art Arfons, set the land speed record in this airplane on wheels. This is a rocket. So they switched from airplane jet engines to putting pure rockets on board because they were being developed in the 60s, a lot more thrust. Smashed the world record of 622. Here's another airplane essentially setting the record. Jet powered, so rockets. I remember back when they were doing this, this one's cool, 2 twin jet engines. Some of these cars would have a jet engine that would get them up to speed, and then they would have a Sidewinder missile strapped to the top. Engine, obviously not the warhead. And then when they got going really fast, then they'd kick that in to give them the extra thrust to go faster. And this is the guy that he generated a sonic boom over land. First time that was ever done in a car. And this is just showing a futuristic car, very streamlined, and an engine on top and a rocket down here. Look at this, 0 to 1,000 in 20 seconds. I don't think this was ever built. This is a concept car, but I just put it in there because it's cool. Here's some color pictures. Here's Ed Shattle's North American Eagle. It's essentially an F-104 starfighter aircraft, again, turned into a car. That's a lousy picture. He had an F-4 that he turned into a car that ran on Shell gasoline. And then this is another car that was competing for some of the records. Notice the huge intake there. And there's another picture of the guy, Andy Green, that set the record. So your book has this in it, which is speed records in the air. So these are airplanes now. And notice as time goes on, speeds got faster and faster. Makes sense, all the way from the Wright Flyer down here, which was real slow, up through a Douglas aircraft and a Ford trimotor, a DC-3, a P-80, some more airplanes. These are conventional airplanes, a MiG-21, F-102. And then there's the Concorde SST, set a record. Here's the F-15 and the F-14. And you would think, well, we just keep making faster and faster fighter aircraft. But notice this, the speeds, top speeds of these airplanes went down. Any idea why? Mobility. But a key thing happened here. A fighter was built that evaded the enemy not by how fast it could go, but by stealth, evading radar. So there's a trade-off between, if you build a stealth airplane, it may not be as aerodynamic as it needs to be, but if you don't detect that it's there, it doesn't matter that it's going screaming fast. And then this curve here, this is kind of cheating because these are just pure rockets. Here's the Bell X-1A. Here's the X-15. And I've thought it was on here, the Apollo moonshot. Does anybody see it? Where is it? Oh, that's right. I put it way up here. I plotted it. So there's the Apollo 10 moonshot, which of course set a really high record. But it's going up through the atmosphere. The air is getting less and less dense, so it's a lot easier to go fast in space. All right, so next time we're going to talk about the speed of sound. How do we calculate it? Because when you're on a commercial airplane, the pilot will come on board and say, we've reached our cruising altitude of 33,000 feet, and we're currently flying at Mach 0.83 at about 575 miles an hour. So is that near the speed of sound? We don't know. We're going to calculate it and look it up. Okay. I'm in the middle of grading quizzes, so I'll hope to give those back to you next time. Any questions or comments? Anything? So I promised some videos. I'm going to do my best to get those in. There's a really cool one about breaking the sound barrier. Chuck Yeager, we're going to watch that. And then there's an aerobatics competition that talks about, well, how do you maneuver an airplane? And we're going to start piecing that in as well. Okay, have a good rest of your day.